haven't introduced myself. My name is Dregas Ryu. I'm the head janitor here. So, and so with that, I'll get off the stage and stop taking Andrea's time. Please, a big hand again for Andrea Barisani. Thank you.
Hi, can anybody hear me? Yeah? Okay, good. Thank you for being here. The first talk is always hard because, many people are jet lagged. I'm certainly jet lagged, which means I'm either very awake for this or very sleepy for this. We're going to find out what the situation is going to be. So my name is Andrea Barisani. I'm the head of hardware security at F-Secure, and I'm going to talk to you about insecure boot. So about vulnerabilities in secure boot schemes. And the next talk from Ilya and Joseph is also going to touch a similar topic. So I'm very intimidated by preceding you guys. So I hope I can set the stage to these kind of issues, which are becoming very relevant into this day and age. So a little bit of background information about myself. So I'm a hacker. That's why I get to use skulls on a slide, which is cool. I'm the founder of a company called Path, which was acquired a couple of years ago by F-Secure, and I've been dealing with hardware since 2005. Which is kind of a long time into the hardware scene. So it was way before the term IoT, Internet of Things, was invented. And we also build hardware and not only break hardware. And this talk kind of touches both aspects of the building and the making, and the reason why these topics are kind of interesting to us. If you want more information about my research, you can find a link there to follow up. So, hardware security is becoming increasingly important for the main reason that while you can have remote software upgrades, you cannot have remote hardware upgrades. So if there are some issues which are embedded into the silicon or the selection of hardware parts, it becomes a very costly mistake to fix them. And this is why some of the issues that I'm going to present about today are becoming very relevant to, and they need to be accounted for before developing a product, particularly when the physical attack surface of a device. So if the threat model implies that a malicious party could have your product in their hands, then these kind of concerns become very, very relevant. And one of the security features which is being used to protect against physical access is secure boot. So secure boot is basically a hardware feature which allows a hardware anchor to be present into the hardware itself, which can be leveraged to authenticate the very first piece of code which is executed by a CPU, by a system on chip. And on embedded system, this happens with the customer keys, your keys, which are embedded into the CPU, and from there on they can be used to only boot trusted code. And this is an essential feature to maintain authentication and also confidentiality when desired on a system which you don't want to be compromised by physical access. So it could be a phone, it could be a gaming console, be an industrial data logger, any kind of equipment where physical possession is a relevant threat. And the secure boot is the very first step into maintaining a chain of trust from the power up to the execution of the operating system and applications. So being a chain, you have several steps, several blocks, and it typically looks like this. You have the system on chip, so the CPU with all of its peripherals configured to host a set of keys which are there stored in an immutable manner. The system on chip verifies the bootloader, so the bootloader is only booted if it's trusted, and then the bootloader has other keys which are now trusted, and these keys are used to verify the operating system. And then the operating system needs to carry on this chain of trust in all this operation. So this is the chain of trust which can be maintained with secure boot. So as I mentioned, we not only break secure boot schemes, but we also implement them. So in 2014, we released an open hardware product called the USB Armory, which is a tiny secure computer in a USB drive form factor. And when we released that product, we also had to implement the secure boot configuration and software for the specific system on chip that we were using. And this is going to be relevant in the talk. We're going to explain why this matters. And now we're doing the same with the second version of the USB Armory. And we're using parts from NXP. In the USB Armory 1, we were using the NXP IMX53. And the USB Armory 2, we're using the NXP IMX6 UL. So this kind of features, we also test them heavily into the transportation vertical. So we do a lot of automotive and aviation testing. We see there are a lot of devices which are secure booted into this domain. Also consumer products, of course. If you think about the iPhone or other phones that use heavily secure boots to prevent jailbreaking, among other things, and also industrial components, when sometimes protecting intellectual property is important, then you also have secure boot schemes, because they are the only security feature which allows to have not only authentication but also confidentiality. So if you want to protect data, if you want to prevent unauthorized access to intellectual property, certificates, and so forth, it all must start with a hardware encode which authenticates the bootloader, which is secure boot. This is an example of what secure boot does. So this is a successfully booted signed bootloader. So we see this is an example on a NXP IMX6 UL. So we have the bootloader being loaded by the CPU. Secure boot is enabled, and so HAB stands for High Assurance Boot. It's the marketing name for the secure boot implementation of NXP. And in this case, we see that the boot process was working. If there will be a violation, so this is an example in debugging mode, because otherwise you wouldn't see anything at all. So when secure boot fails, the CPU refuses to boot any code and to give you any output. In verification mode, which is kind of a test mode, so that you can try before enabling it, this is what it looks like. You see that there's a failure, and so the bootloader is not loaded at all. The bootloader, once loaded, is then responsible to carry on the chain of trust. One of the implementations for this by the U-boot bootloader is called verified boot. And here we see the later steps. It's important to understand that this step has no dependency on the first one. You can have a completely different set of implementations for implementing the next steps of the chain of trust, completely independent from the first step. One of the reasons for using secure boot is because also it unlocks you the use of very specific security features later on in the runtime. So secure boot is a boot measure. It doesn't prevent loading of untrusted binaries at runtime. It is something that only happens at boot time. However, there are other security features which are then later on used at runtime. So one of these, so this is the set of security features in a typical system on chip. This is the one using the USB Armory 2. We have two random number generators, cryptographic accelerators. We have RAM encryption, but we also have something called secure non-volatile storage, which is a feature which can only be used if secure boot is enabled. Because this feature allows you to use a specific, unique hardware key, which is different for each device, and enables you to encrypt and decrypt data so that this process can only happen on that specific device. And this is one way to obtain confidentiality on data which is stored on this device. And the only way to use this key is when secure boot is enabled, because the CPU will refuse to give you access to the unique key if trusted code is not being executed. So every time you have an embedded device which is left unattended, so there's no screen or keyboard, and you need this device to load encrypted data in a manner that can happen securely, so that there's no way that if I get a physical access to this device, I can intercept this process, then using secure boot and a feature such as this one is the only way to achieve that. because even if you use external security elements, communicating to those security elements in a secure manner, it is very difficult if you don't have secure boot in place. We also developed drivers for this, so this is one example of the driver that we implemented for the USB armor for this, and it basically looks very simple. You have one tool for encrypting a blob of data, and you have the same tool you can decrypt a blob of data. And this can only happen on the same unit. If we do the encryption and decryption on two different USB armories, this will fail because the internal key is different. So with these features, if we put all of them together, then a full chain of trust can be maintained because we have the CPU holding the keys for secure boot, which are fused by the customer. It's a one-time irreversible operation. Once it's done, you can never undo that process. So the CPU authenticates the bootloader. The bootloader, which is now trusted, is another set of public keys inside used to authenticate the operating system, in this case the Linux kernel. The Linux kernel carries on let's say in this example, a decryption procedure. And this decryption procedure, since it's trusted, it can now ask to the CPU, again, using the feature I mentioned before, to unwrap, so to decrypt some key material, which is stored there on the media storage. And once this key material is decrypted, then it can be used to do something like unlocking an encrypted partition. So this would be one example of using the chain of trust and the secure boot anchor to have authentication and confidentiality on an embedded system. By having secure boot, as I mentioned before, you can also securely communicate with external security elements. One of the reasons for doing so would be, for example, to have monotonic authenticated counters, which are the only way to prevent rollback attacks to happen. A rollback attack is when I desolder, let's say, a flash memory, and I replace it with the contents of an old one, because maybe you had a firmware that at some time had a security bug. But you're really good, you do software updates, so that bug is not there anymore. However, I do have previous images which were signed, and so they were trusted by secure boot. So the only way to prevent me using an older version of the firmware on embedded system is to use these external monotonic counters, because then you have a chance for the firmware to check if they are supposed to run on that specific hardware, because they can check this counter. The only way to securely communicate with these external components is by having a secure booted machine, which can hold a key securely, which can be used to communicate in an authenticated manner with these external monotonic counters. There are other security features which can only be securely used in these kind of devices when you have secure boot, but they have a different purpose, which is maintaining the runtime isolation of components. So as I mentioned, secure boot is a boot time security measure. Something like ARM Trustzone is a runtime security measure, which provides further isolation between two worlds, the so-called normal or insecure world and the so-called secure world. And these are features that only make sense in pair with secure boot. Because if you're using Trustzone to protect keys, because you are delegating key management into the secure world, it only makes sense to do if you have secure boot. Because secure boot is the one that gives you the chain of trust that allows you to put trusted code into the secure world. Without secure boot, the secure world would not be secure against a physical attacker. So now I'm going to present a few case studies of what can go wrong at different stages of the chain of trust, growing from the higher level to the lower level. And I'm going to start with Trustzone because I just mentioned that. And the emphasis here is that given that we have a chain of trust, it takes a bug in only one of these elements, in one of these blocks of the chain to completely mitigate the existence of secure boot. So let's say that you're using Trustzone to implement some complicated isolation principles. one of the things that Trustzone is supposed to prevent is memory access from the insecure world towards the secure world, because you want to maintain these two environments completely separate. And so one of the things that Trustzone does is it prevents DMA, direct memory access, by the various peripherals which are not authorized to access one of these specific worlds. You can think of Trustzone as a sort of hardware firewall that you can decide to configure depending on each case. And there are some cases where, in this example, this comes from a project called GNodeOS. So in this case, what they wanted to do was to isolate the GPU, so the graphical processing unit, and the image processing unit between the two different worlds. But there's a design flaw here, which entails the fact that the granularity of the policy that you can set is inconsistent, because the access of the source access from one of these devices can be set with a different granularity opposed to the destination access to one of these devices. So what happens here is that this use case is impossible to achieve, because by reading the fine prints of the reference manual, you realize that the GPU and the IPU, they share the same master ID. So if you grant different accesses to one of the two words, you are implicitly also granting cross-domain access to one of these devices. So this is an example of a design flaw that, if encountered, it will completely mitigate all of the isolation that you have implemented. This is just one example of a software issue that can happen. But if we go down into the hardware, the most critical findings that you can ever find are actually hardware findings. Because while a finding like this one can be somewhat mitigated by software, or at least accounted for, if you add a problem in the silicon itself into the actual CPU, then the only solution is to replace that part. And if you have hundreds or thousands or tens of thousands of millions of devices out there with a CPU which has a security bug in the silicon, it's a very, very costly issue to repair, if assuming that parts are available. So this is one example that affected us. So we built the USB Armory Mark I using the IMX53 CPU, which was supposedly supported long-term by NXP, so for 20 years. And in 2017, security company PacSec discovered two critical vulnerabilities into the way secure boot is implemented into the IMX6, not the IMX53, but a very similar part. So we know them very well. They contacted us, and we investigated whether these two bugs will also affect the IMX53, and they did. And these two findings, there were basically parsing errors in the way certificates are being loaded from the image, which is a step which happens very early at boot. So there was a buffer overflow. You could completely bypass the process. And in our case, we got hit by the fact that the long-term support for this part didn't entail security, apparently. So NXP would not release any updated part number for the IMX53. So what we did, we released an advisory. We pushed for an early release, where it was done in actually two stages. First, we warned our users that the feature was broken, that you could not use it. And then after the embargo date was over, we also released the technical details on the findings. And not only that, but we also released a proof of concept that allowed users to test and exploit the issue. Because being a company that is in this position where we make open hardware security product, or we're also tester, we really want to develop the tool that would allow people to break into our own product, which is kind of weird, but this is the way we thought it was right to do. So our tool, we have an open source tool for signing images, which is the only open source implementation of NXP HAV, and it's now also the only open source implementation to break HAV. So I wrote a blog post about this if you want to check it out, where we reason and explain better these principles that we follow. So in the tool now, you can use it to sign images. But you can also use it to sign images with any certificates if you want. And this was really important for us to really understand the impact of the finding, to make sure that we understand exactly what would be the state of a unique compromise into this manner. So for instance, one question might be, if I compromise secure boot with this tool, with these techniques, am I left into a secure state where I can use the unique hardware key? And the answer was yes. So, and the only way for us to be sure was to actually test it. And the message that we wanted to broadcast was that if there's a finding, if there's a bug, but there's no proof of concept, there's no weaponized exploit, so to speak, it doesn't mean that you are more secure. You should always assume that somebody has the exploit. And in fact, it took us less than 2 days to develop this proof of concept based on the contents of the original advisory. And we really wanted to prove ourselves to understand how difficult it would be to weaponize the technical text of the advisory. And it took us less than 2 days. So that's the important message. One of these two findings concerns loading from USB. Because in USB, on these kind of system on chips, often from USB, you have a way to upload firmware onto the device. One of these findings concern that specific attack surface. So it is important to limit the attack surface as much as possible when a system which is secure booted. So to help this process, we developed a tool called Crucible, open source tool that allows you to easily set the one-time programmable fuses which are required for secure boot operation. So for instance, when you enable secure boot, when you fuse your keys into the system on chip for secure boot operation, you need to use one-time programmable fuses. And often this process is very complicated, is very error-prone, and if you make a mistake, you will break a device. I know. I have a few bricked USB armories of my own. So we developed a tool which, first and foremost, provides you nice ASCII art for visualizing the fuses. That was kind of the only motivation for me for doing it. But apart from this, it also allows you to very easily to blow a fuse and to read back a fuse with very easy operation. And as a standardized way of defining the one-time programmable fuses format, so that it's easy to convert the reference manual to the metadata required for doing the fusing, and you have one unique way of describing them instead of having to read a manual, then use a low-level tool to burn the fuses and do this risky operation. And this was also important for us to give people a reproducible documentation so that they can actually cut and paste commands to lock down their systems. Because to reduce the attack surface of the system on chips, there are several fuses that you can burn to disable things like JTAGs, to disable vendor-specific reserved modes, to disable the method that allow you to load a firmware from USB and so forth. So it's important that when you enable secure boot, you also lock down all of the debugging features as much as possible. Because you might be locking down the OS, like the runtime software, but maybe you left open some very critical debugging mechanisms or boot modes, which can completely bypass secure boot mode. So it's important to have tools that easily allow you to do that with confidence, not with fear of breaking a device. So as we got hit by this security bug for the USB Armory Mark I, so this not only gave us great motivation to do a second version of the USB Armory, but it also gave us motivation to do a security audit of the system on chip that we wanted to use for the USB Armory Mark II. So we went through not only an internal audit of the boot run of the part that we wanted to use for the USB Armory II, but also we went for a third-party security audit of not only the hardware side, but also our own software chain of trust. It was really interesting for us to be, for me actually for the very first time, on the other side of security audit. Because I would ask another company to do security audit of the software that we developed, and I would receive a report on that. And it was very interesting because it was the first time we would be in that situation. So we and the third party did not identify any further issues in the boot ROM, which gave us the go to use this part for the USB Armory Mark II. We found a few issues in the actual kernel modules, the drivers from Freescale NXP that were there for using the cryptographic elements. So this is software, not hardware, and this also motivated us to do our own forks and cleanup and our own kernel drivers, such as the one that I showed to you before. And then we also took a look at the bootloader, because the bootloader is the second block of the chain of trust. First you have the boot ROM of the system on chip, and then you have the bootloader, and we look at U-boot. And pretty much everywhere we looked, there were issues with the bootloader. So that's what kind of the state of things. So we had some findings, and these findings were, these are the two most critical ones, but the comment that we had both in the internal and external audit is there might be many more. So this is the next case study for U-boot. So we identified two bypasses of verified boot that they pretty much touched every single mechanism that U-boot has for loading a kernel, because they were affecting the way you would load a kernel from the file system, which is the first thing that happens. You have your trusted bootloader, and you load the kernel typically from the file system. And the second bug would be on loading kernel from the network, because you really have two ways. You either load the kernel from the file system or from the network. And both these methods would lack any boundary checks. So if you would present a kernel of a certain size, you would overwrite the memory of U-boot, and you would really easily achieve arbitrary code execution. This is an example of loading an image from the file system, and then you're just there in the stack, or you load it from the network, and you're also there on the stack. So very trivial. And these were very difficult to patch, because U-boot does not have awareness on how big his stack is going to be. So it's very difficult to set limits, because it has a lot of plugins that use memory in a very different way. So it's really difficult to set a limit. What you can do, if you know what the size of the kernel is going to be, then you can put an argument into the command line, and you can use that to make sure that you're not loading an excessive amount of data. So luckily enough, at least there was a workaround for the file system command. For the network command, the workaround was disabling network commands. So that was it. But luckily, network commands are typically only used in provisioning at the factory, which happens before secure boot, so it wasn't a big of a deal there. Then, after a long series of patches, these issues were both fixed in version 2019-04, which is the version scheme for U-boot, and so now these issues are fixed. But again, it is important to understand that there are many stages in a trusted boot scheme, and all of them can go wrong. And if any of them goes wrong, then you have a problem. Last but not least, a case study on a completely different part, which is Xilinx Zinc UltraScale plus FPGA. It's a system on chip with a built-in FPGA, and this is another example to show you that issues concerning the hardware are not rare. In fact, as part of our audits, we now often, so every time we do an automotive audit, for instance, we have secure boot. We don't limit ourselves into checking the code of the customer, but we also push for actually testing the boot ROM and the hardware implementation of the third-party vendor. And I can tell you that there are at least 2 other cases where we're not allowed to disclose, because right now those findings are locked into our relationship with the customer, which is something that we're really trying to, in the future, to have provisions to get out of, because we think it's important to release these findings to the security community. And in one case, we were allowed to present them, and this is the one that concerned the Xilinx. But this is just to say that there are many more, because the state of security of these boot ROMs is very primitive. The bugs that were found into the NXP case, and also in this one, if we would had access to the source code, we would spot them immediately. And it takes, of course, much more time to test them practically, because you need to learn how secure boot works, you need to be in a position where you can sign images, you need to set up a debugging environment. So even triggering the simplest buffer overflow or doing fuzzing takes some effort, takes days or maybe weeks. And these findings would have been found with a single grep on a command line on the source code, which also means that the vendor itself would have probably done a little more due diligence in those cases. And so, given that how common these are, I would say we always say that the state of hardware security, embedded system security, is, you know, like software 15 years ago. With boot ROMs, it kind of feels that it's even, you know, further away. So in this case, what happens is that we found two flaws just by reading the documentation. And later, it took us some time to actually verify them on the development toolkit. But these findings, you can read the documentation and you can somewhat gather that something is going on. So the Xilinx part has two secure boot modes. One called the root of trust, which uses asymmetric cryptography, and one which uses symmetric cryptography. And of course, since symmetric keys are somewhat easier to manage to most vendors, that's in certain fields the preferred method. And this is the encrypt-only secure boot, where you have encryption only as a secure boot mechanism. And there are some pieces of metadata. So the encryption that I use is authenticated encryption. However, there are some metadata loaded early on which are not encrypted and therefore also not authenticated. But this metadata includes execution addresses for where to jump to in the firmware once the boot process begins. So you end up in a situation where you have a payload which is encrypted, but you can control where to jump to into that payload. And this, of course, in the end, with a series of gadgets, a chain of gadgets, leads to arbitrary code execution. And there are actually two separate issues, two separate metadata here that allows that. One is in the boot header, and one is the partition header. The first one, the boot header one, is parsed by the boot ROM in the hardware. So there's no fix for that. The second one, in the partition header, is parsed by the first bootloader. And the vendor didn't want to fix even the second bug, because they declare, okay, this is the way it is. And again, this is another issue where there's nothing you can do if you use one of these modes. Luckily here, you have an alternative secure boot mode, which is the hardware root of trust. So by completely changing the way you're using this feature, this can be mitigated. But as it is, the encrypt-only secure boot mode of these parts cannot be securely used. And Xilinx was actually very responsive about this. They had no issues into public release. They released an errata for this, and they also changed the reference manual, where before they would not hint about any of these issues. And now they explicitly say that without authentication of these headers, anyone can modify the control fields, resulting in an incorrect secure boot behavior. So now they explicitly state into the secure boot documentation that the secure boot behavior is incorrect, which I think is commendable for a vendor to release this information in a reference manual. Just to give you perspective, as of today, it is almost impossible to find information other than our advisory and parts level advisory for the NXP issues for secure boot. If you go into the official errata for NXP, you're not going to find any information about them. And in fact, we emailed them telling them that maybe after 2 years they should put something there. And we ended up in situations with customers where the first finding on our report was simply due to opening the case of a product and looking at the part number, the revision, and they were vulnerable. And the customer didn't get this information from anyone. And unless you're familiar with these kind of findings and you know how to search for these issues, you're not gonna find information, because engineers, and rightly so, they go to nxp.com, they go to the part page, and they check the errata. That's the only thing that they do, and they're right in doing that. They're not going to Google for CDs. They're not going to think that there's going to be anything wrong with secure boot. So then they purchase the part, and they have thousands of devices with a vulnerable part. And then they come to us, we do an audit, and we find many findings, so they're already depressed. But then they also see that one of the findings is because their part was IMX6 blah 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 AA and not AB. You know, and when you buy the parts, if you don't know about this, you're not going to notice. And so you end up with a lot of devices which are just vulnerable. And even after maybe implementing a lot of, you know, very good secure boot chain of trust mechanisms, which now are useless. So all of that development time is wasted. So this is becoming an increasing concern, and especially also in the world of automotive, where for a lot of regulation and compliance, or maybe just purely intellectual property concerns, you now have ECUs or infotainment system, a lot of parts which need to be secure to protect your data, to protect the customer data. If you end up with a part which has one of these bugs, then again, there's no remote software upgrade. Sorry, there are remote software upgrades, but there's no remote hardware upgrade. So that can become a real problem. So the key takeaway, I guess, is that when you implement and when you invest time in implementing a chain of trust, you need to account for each and every phase, and this also includes code which you don't control. So the code of the third party that is giving you the hardware. And the strongest hardware or software security measure can be broken just by the smallest mistake. And it's also important for us to do public responsible disclosure of these findings, because I think hardware findings, low-level hardware findings, are now often overlooked. This sort of implicit trust in the fact that your vendor is going to provide you a hardware security feature, which of course is going to be secure. But this is not the case, because the quality of that code will be the same, if not worse, or much worse than everything else that you're going to put on that board. And it's time to make people aware of this. So it's important to audit the very early stages and the neutrons of these kind of parts. And so if you spend your budget into auditing the software that runs on an embedded board, if you have secure boot, you should also invest into auditing the hardware itself. Because not only the vendor is not guaranteed to have a secure implementation, but they're also guaranteed to give you fixes, like in our case. You know, despite long-term support for the IMX53, they were like, sorry, we're not going to give you any updated parts, you need to change your design, which sucks. So it can be really bad. And understanding the way the software and the hardware interact is really, really important, like in the Xilinx case. So we have another project that we actually just launched a few weeks ago, which aims to reduce even further the attack surface of these systems. Because if you invest a lot into using these features, then you might end up with a complicated setup where even if the task that you're doing is really simple, let's say that you have, I don't know, a cryptocurrency wallet, something which, I mean, the task is fairly complicated, but usually the implementation is very well defined. You need a piece of code which signs transactions, and that's it, and have some interface. And we often find ourselves in a situation where we have very nice firmware, very minimal, few dependencies, but then we have to carry over the entire Linux kernel and all of its drivers, because in order to decrypt and launch our firmware, we need a OS with all of its drivers. And it might be that we're using a high-level language for our firmware, but then we're carrying over tens of millions of lines of code from open source libraries, the runtime, and the Linux kernel, which then we have to maintain. It could be that our firmware needs to be updated maybe once in a year, but then we need to update every month the kernel that's underneath. And we do a lot of effort to provide also for the USB ARM a very minimal runtime environment. We have a stripped down Linux kernel with only the required drivers. We have a runtime which is a very minimal run, this 1 megabyte of size. So we strip it down as much as possible, but it's not elegant. We carry a lot of code that we just don't want. And the more code we carry, the more chances our secure boot chain of trust can be broken at runtime, because there's a bug maybe in the USB driver, or in the TCP/IP stack, or in the way things are linked and into runtime. So we wanted to do something about it, and we created something called Tamago. So Tamago is a framework which allows you to easily launch unencumbered Go applications without an underlying operating system. And the reason why we picked Go, of course, I mean, languages is a big debate about them, whether you like it or not, but in our case, we saw that both because the cryptographic library is really good and really trusted in Go, both because it's a language that really, I think it suits a lot of use cases for the firmware that we develop, especially in the cryptocurrency world. We often found ourselves in a situation where we had all these Linux setups to launch a single monolithic Go binary that would do everything. And we wanted to be able to launch that Go binary without the operating system. So we created Tamago, which is a minimal modification. We're actually talking about 3,000 lines of code to the Go compiler, where we can make a Go application to run on their own, on the bare metal. And we write the drivers in Go, which makes for a dramatically reduction in the line of codes count. This code which you can actually read, because try and read how to change the clock speed in the Linux kernel and Go, and then we're going to talk about it. We can have very complex firmwares without any single line of C code. So in this example here, this is a USB armory booting up, initializing the random number generator, deriving a key using the secure non-volatile storage function that I mentioned before, sleeping for a while because we're testing the clock, deriving random number, signing with electric core cryptography a Bitcoin transaction, all of this with different Go routines, and then shutting down. And all of this was done without a single line of C code, except for the bootloader, which, however, goes away after you boot it up. And with modifications to Go, which are minimal, and with a clear separation with the modification in the compiler, and everything else, all of the drivers are not in the compiler, they're outside, provided by us. And the way we achieve that is that whenever we need a system call, we just implement that behavior within the Go runtime itself. So we completely remove the operating system, and we have a Go application which relies on two Go packages, one for supporting the system on chip, and one for supporting the actual board. And our Go package can be coded without any knowledge of this. This is the key takeaway. Your code doesn't need to be aware of this, with the exception of importing one package, which in this case is USB Armory Mark II. So you import that in your Go app, and then you write your Go app and you be married. The only reason why we also import IMX6 here is because we want to use the specific key derivation function from the IMX6. All of this is open source. It's early stages of development, but it's already working, running fine on the USB Armory, and we also plan to support more boards in the future, because it's actually fairly easy to add support for different boards. So I really hope that soon we can also support the Raspberry Pi, as it's very popular, and even more boards and more drivers. So I'm now writing a USB driver for Tamago so that we can do communication over USB and so forth. And it's a very good exercise. And also, if you want to learn about system and chips, in all our drivers, every time we do something that touches the hardware, we put a link to the reference manual with the page number to the reference manual, whether it's the ARM architecture manual or the system on chip manual, so that you can understand what's going on. And the reason why I do that is because I wish that would be done in the Linux kernel. But it's never done. So I need nice comments where I can go to and check. So I thank you very much for your attention, and I think we have time for questions. I'll be very happy to take any questions that you might have. Thank you very much. Dominic Gazes.
I'll start that question. So So your the U-boot binary boundaries vulnerability, was that something that was specific to the NXP architecture, or is that just do all the U-boot architectures suffer from that boundary check issues?
Right. So what I mentioned is that the way verified boot is implemented is completely independent of what happens before. So those findings affect any architecture and any board and any hardware that uses loading.
Oh my gosh.
Yeah.
There should be much more visibility to that issue is my comment.
Yes, I agree. And also, if somebody wants to have fun and find more bugs, there's a lot of file system parsing that U-boot does because they support different file systems. I'm sure that if you go and play with that, you're gonna find something. The code quality is not great, and I always don't like to say that. I do appreciate open source projects. I think it's amazing that we can do all of this with open source. So I think U-boot team has a lot of burden in supporting a lot of architectures, but yeah, there should be more emphasis on security there.
My concern is that there's a lot of people that use U-boot in a lot of places. So
Yes.
Billions of devices.
Yes.
That's a big deal.
And they also don't update them very often. So
Yes,
these findings.
so you need 219.4
Yes.
is the new one.
Yes.
Okay.
Yeah, or you need arguments where you explicitly set the size of the kernel, but they're not that common because people just load the file from the flash because maybe you're not going to.
Is there any blog post or an advisory?
There's an advisory for it. Yes, they're actually, I think, yeah, because our advisory out, I think you could also put an announcement on it. But yes, it's not broadcasted as much as it should be.
I think that,
Yeah.
I'm going to go tweet that out later.
Yeah.
That's more people need to know about that. Any other questions?
Thank you. I believe this may not be specific to your work, but one question that popped up was during the description of the SOC, specifically the way that a key is stored, I believe it was the CAM key stored inside of the SNDS. I noticed that it's stored via AES ECD. Would you be willing to expand upon why that is acceptable in this context?
So the way you use these techniques. So first of all, a system on chip would only expose you the very basic AES modes, and then it's up to you to implement the additional modes because you can actually do it. Even if you have, if you have ECD, you can decide to the way you encrypt the blocks. You can decide to put the IV at each block and implement other modes. The second thing is that while the hardware support allows you to encrypt multiple blocks, we only use it for key derivation. So we only have one block to encrypt, right? But yes, you need to be careful about it. Yeah.
Thank you. That was awesome. I have one statement and also one question. But one thing I just wanted to say, thank you for mentioning the responsible disclosure, because I've been yelling about that for like 2 years now, where I feel like there's no real way to responsibly disclose a hardware bug that can't be patched because the vendor's never going to agree to disclose it.
Yep.
And at what point is it considered responsible for you to drop it out there?
Yep.
And I think it's something that needs to be discussed. And then one thing, just a question about your experience doing hardware audits, and you mentioned burning fuses, and I imagine you see a lot of devices that use fuses to protect against downgrade attacks. And I was just curious, have you ever stumbled into a situation where you could maybe initiate an update and let it burn a fuse and then stop the update and basically just go and burn all fuses and then now downgrade to the release or something?
So I'll respond to the last question first and then the statement. Yes, the atomicity of operations is quite critical when you burn fuses. So it's always important to make sure that you burn the fuse either before, depending on how you're using the fuses, either before or after you're doing your process, so that worst case scenario, the device is break. It's better to lose the device rather to have a device which is in a state which is insecure. But it's tricky to do. In automotive also what happens sometimes, in automotive secure boot works in a slightly different way. because they have performance issues and they want to boot as fast as possible. So secure boot happens in parallel. So you boot the code, even if it's untrusted, and then you have a separate core, which at some point verifies what was loaded into memory, and it will stop everything if it sees that this code wasn't authenticated. But you cannot afford to check first and boot later. You boot at the same time, and then at some point you check it. And that's also when you can encounter problems with, if your malicious page will payload to do something before that happens. So there's a lot of situations where you really have to be careful. So yeah, this is a very valid concern. Typically, using fuses for downgraded attacks is not efficient because you don't have a lot of fuses. Let's say that you have 128 bits of fuses, like for customer, then you get 128 for routers, right? So usually you use external components because they have monotonic counters where you have like maybe 8,000 or 10,000 tries. So that's also one way to deal with that. It's kind of easier to deal with the atomicity of that process if the component is external. Like when we use VMware, we actually have two. We have two external components where you can add monotonic counters. So you can use different schemes to use that. You can also use, fun fact, you can also use the flash. The flash memory has something called replay protected memory blocks. You can share a symmetric key between the CPU and the flash memory, and you can have one sector of the flash memory, which you can only write if you know that key. And that's also a piece of storage which can be used to store counters. Maybe they're not monotonic, but at least you have an area which is outside the system on chip in the flash, so that you can make sure that if I actually desolder the flash and replace it with another one, things are going to be different. You can correlate the counters. Responding to your first statement, yes, there's a huge debate on what responsible disclosure means, right? Once upon a time, the debate was, where do I do full disclosure? Which makes it. Right now, it's all about who do I sell the bug to, or do I do responsible disclosure? Everybody has its own philosophy. In my view, sometimes I think it's a very old school view, but anyway, if you, as the customer, are at risk, you're going to be at risk because the bug exists, not because the bug is being published. So it is my duty to make sure that that information gets out public. And if there's no fix, it is one more reason to release that as soon as possible rather than later, because I know there's not going to be any fix. So you shouldn't wait at all for knowing that information. And of course, this is controversial, right? A lot of people, especially a lot of companies, they don't understand why this is the case. And you always have to mention history and show the cases where it was beneficial for the customers to do so. When we released our proof of concept, NXP didn't understand why we would want to release a proof of concept, nonetheless, for our own product. But in the end, I think it was the best choice. It also motivated us to a certain way. Following our own code of conduct as tester, and also being in a position where we develop a product, it was a bit conflicting, but one part was really overwhelming. So we have to release because this is what we do. And it motivated us to do a better product in the end and to do the audit. So in the end, I think it can only be good. But I can see how that's not black and white for those things. Okay. Any other questions?
Yeah, just a quick question. You mentioned earlier that you would be concerned about potential parsing or replicating file system parsing. Just wanted to ask, is that for your mitigation reason, or?
Well, no, it was referred to the bootloader has to do a few things, right? Loading a file from the file system, putting it in memory, and executing it. What we found was in the putting in memory part. But then there's a whole parsing that happens before because the image has to be read from the file system. And there are many file systems which are supported by the bootloader. Certain file systems are really easy to parse, like VFAP, for instance. Some other, not so much. And so if you will find bugs where complexity lies. And in a bootloader, complexity lies there as well.
But the image would be signed, right?
It doesn't matter, the parsing of the file system happens before.
So the image would be signed first, so you would, as an attacker, you would need to forge the signature first.
No, because if you have a signed image on a file system, if I need to read the signed image, I need to parse the file system first.
That's my question, is real identification. not, you're saying. You first need to parse the files. And
Of course.
You don't put that, so why would they not authenticate the image in itself? So as binary to start.
Because in order to find the image, you have to, in order to authenticate the image, you have to put it in memory. In order to put it in memory, you need to know where it starts and when it ends. So you need to know where it is. And you need to parse the file system for that.
Okay, we could take it offline, but I could imagine other ways of storing that information.
Well, yeah, there are many ways, but those are not implemented in
Okay.
Ubuntu. Yeah, okay.
Yes.
Yeah.
Thank you. Any other questions?
Yeah, I got one.
Oh, God. It's going to be a tough one.
Uh-oh.
I was very impressed at the end with Tamago.
Yes, oh, thank you.
The fact that you cut out all that millions of lines of lazy C code is impressive.
Yeah.
It does. I played around a little bit with Go, and it's got many good parts, but my point of view from this perspective is that it comes with a runtime,
Yes.
and so, which is partly implemented in C.
No.
Some of it is.
No.
When I last looked, some of it was.
No, now. Now Go is compatible with Go.
Is it entirely written?
You have some assembly.
Okay, so my point was, A, doesn't that put a lot of pressure on the runtime? And then number B, is, especially because you're doing crypto operations.
Yeah.
I looked at how to scrub memory, and doing it from C is really hard. Doing it from Go is nearly impossible.
Mm-hmm.
Do you guys have libraries? Like, how do you try to scrub memory when doing crypto operations in Tamago?
So first of all, one of the things that we promote is to actually use the crypto elements inside the system on chip. So we're going to implement drivers for that. And for those, the crypto elements, they have ways for staging memory so that they have the concept of red and black memory, so they will be protected by you. The second thing, yes, scrubbing memory in Go is difficult, but it can be done. If you keep the same object for the key and the right key, you can wipe that same object so that you don't have to wait for the garbage collector to do it for you.
So it's some kind of pinning?
Yes.
Okay.
The runtime, so there's this classic debate of you have a runtime, you have garbage collection, it's bad, it's bad, it's bad. If you actually read, because I read a lot of Go compiler code to implement this, as you can imagine, it is fairly clean. And the reason why you can do something like this in only 3,000 lines of code is because the runtime is clean enough that it allows you to do this. And it's a fairly simple garbage collection scheme. There are so many comments in the code. It's difficult to convey to you this feeling because I have a lot of familiarity with it, but I do trust the runtime very much. I wouldn't do, like if we're in the automotive world and we need to do real-time operation, of course, it's not the ideal way, but if I'm doing a cryptocurrency wallet, I don't care. It doesn't need to be real-time, right? Especially if it's for personal uses. And I would say that as long as you care about protecting the memory, then you're fine. But you also have to think about this scenario. First of all, you can have a USB armor with RAM encryption happening by hardware on the bus. So cold boot attacks completely mitigated, right? Second of all, the reason for using Tamago is that you're going to run on a single user. It's not any user, single application. It's not like a smart card where you accept the fact, or a phone where you accept the fact that there's going to be untrusted application. It's only going to be your application.
Right.
And since it's written in Go, we eliminate the possibility of buffer overflows or those kind of issues. So you really have to mess it up. So it kind of lowers the need for protecting memory.
Yeah.
You see what I mean?
Yeah, absolutely.
So, and also when we do cryptocurrency stuff, we always promote system where you are into an escrow schemes, where you need more than one party to sign something, so that one single device doesn't have the keys to the kingdom. So there are many ways to approach that. And if you don't want, you just use the driver and use the cryptographic element. So I would say make it a little bit better for that. And I know that there's an effort also in Go to provide safe, easy way to scrub memory. So there's an ongoing discussion with that also with Filippo Valasorda, which is doing a lot of, it's the crypto gopher, so to speak. So, you know, I think it can only improve.
Okay, awesome, thank you.
Yeah.
Speaking for myself, I'm pretty excited to get my new USB armor in.
Yeah,
Check out
thank you.
Tamago. It's very exciting. Please, a big hand for Andrea.
Thank you very much.
This morning, you may have noticed that we are actually booting up the conference because the first two talks are both about boot security, because if your boot is insecure, it's pretty much game over for the rest of everything. So we'll switch over to the next talk, which is also about boot security, and it's really, I think, one of the most fundamental issues that's facing us, and we aren't paying enough attention to it. Thank you. Well, give us a few